Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about what's so funny about quantum mechanics. These What's the Big Idea screencasts are intended to highlight the big ideas behind the material that we'll be talking about in Physics 323 this term. And for the first episode of What's the Big Idea, we're going to be giving an overview of what our goals are in Physics 323, advanced topics in quantum mechanics. And one of the very first things I'm going to have you read is a book by a very familiar author, David Griffiths. David Griffiths is the author of the textbook that you used in Physics 302, and he's also the author of a popular textbook that we use in Physics 314, Electricity and Magnetism. And those books are written for very sophisticated students. They're 300 level students. But this book that Griffiths wrote is intended for non-experts. It's really for people who've never taken a physics course. And it's called Revolutions in 20th Century Physics. And there's a chapter in this book entitled What's So Funny About Quantum Mechanics? Or actually, it's a section of a chapter. And it really encapsulates in very non-technical terms, the central ideas of quantum mechanics. So before we delve in a very sophisticated manner, we're going to talk seemingly qualitatively, but the ideas that are described in this section of the book called What's So Funny About Quantum Mechanics are very deep indeed. So let me give an overview of what's discussed in this section of the Griffiths book, and more broadly, what we're going to be discussing in Physics 323 this term. So we're going to be talking this term about quantum particles, particles that obey the rules of quantum mechanics, particles such as electrons, or actually primarily in this course, photons. And another thing which I'm going to have you watch in this case is a famous lecture by the great American physicist Richard Feynman. Feynman, again, very deep thinker, really contributed in a fundamental way to our understanding of the rules of quantum mechanics. Feynman was also a great communicator for non-technical audiences. And in the early 1960s, he gave a series of lectures at Cornell University intended for a non-expert audience, non-technical audience. And there was a lecture about quantum mechanics, and it's a wonderful thing to watch. He's really quite charismatic in his own way. And he talks about the behavior of quantum mechanical particles like electrons or photons. And one of the quotes in this section is that quantum particles behave in a way that is nothing like what you have seen before. Your experience with things that you have seen before is incomplete. The behavior of things on a very tiny scale is simply different. And it helps to remind ourselves at the beginning the fundamental ways in which quantum particles are quite different than anything that you encounter in your everyday life. And they sort of require, if you're going to think about them, a sort of reorienting of your brain to help you think about them and realize the ways in which they are fundamentally different. So, what are the ways in which quantum particles behave differently from things that we're familiar with in everyday life? Well, one core feature of quantum mechanics is this idea of indeterminacy, that things are not either or, they can exist in what we call superposition states of being two different things at the same time. And this idea of indeterminacy and superposition really troubled a lot of physicists, continue to trouble a lot of physicists, really, but a famous physicist who was deeply troubled by the notion of quantum indeterminacy was none other than Albert Einstein. Einstein, of course, helped found quantum mechanics. He came up with the idea of the photon, but he was also deeply troubled by quantum mechanics. And a famous quote of Einstein's that gets at what it was that was so unsettling to him about quantum mechanics is the moon there when nobody looks? Einstein thought the answer was clearly yes. It didn't have to be that you had to measure or observe the moon for the moon to have an objective physical reality. Um, Quantum mechanics, as you know, on the other hand, really says that at least when you're dealing with quantum particles, things at a very small scale, the answer to the question about whether things exist before you look at them is much more subtle. It's sort of no in a way that they don't that the physical reality doesn't take on a definite state until you make an observation. So we'll talk this semester about this famous paradox, Schrodinger's cat, in which Schrodinger imagined a system consisting of a cat and a vial of material that poison that could be opened by the decay of a radioactive atom. And a quantum mechanical description of that state is one of indeterminacy. Before you open the box to see if the cat is dead and the atom has decayed, the system can exist in a superposition state of being partially with the cat alive and the atom undecayed, or partially in a state where the cat has died due to the decay of the radioactive atom. And at the macroscopic scale, this seems absurd that the cat can be both dead and alive at the same time. But at a microscopic level, quantum mechanics says no, that this is really the way we describe things, this indeterminacy. So in Physics 323, we're really going to try to get in a deep way at understanding paradoxes like Schrodinger's cat and what the experiments about the world tell us about the way to think about such a system. Another core part of quantum mechanics that's really funny, really weird, is this idea of entanglement. What do we mean by entanglement? Well, in Physics 302, you generally dealt with systems consisting of a single quantum particle, like a single electron. Uh, and Physics 323, we're going to extend consideration to multi-particle systems. So in particular, we're going to use photons as our particles, and we're going to imagine situations, actually situations that we can achieve experimentally right down in our own laser lab, of a system of two photons that are entangled. And what do we mean by entanglement? These photons can have polarizations, and the polarizations can be horizontal or vertical. And we're going to describe an experimental situation in which we create photons that are in this superposition state of being either both horizontally, when you measure, you either find both the photons are horizontally polarized or they're both vertically polarized. But before you measure, they're in a superposition state of being some combination of both being horizontally polarized and both being vertically polarized. And a quantum mechanical description of things says that it's the act of making a measurement of one photon's polarization that causes a collapse into either this state or this state. And that is a pretty weird notion because it makes it seem like making a measurement on one particle has an instantaneous effect on what you're going to observe for the other particle. And this aspect of quantum mechanics really freaked Einstein out. He referred to this situation as a spooky action at a distance, and he wrote a whole paper with Nathan Rosen and Boris Podolsky, a paper about sort of saying that this aspect of quantum mechanics, these spooky actions at a distance, really made it clear that quantum mechanics was not the final story, that there had to be some objective reality about things that quantum mechanics was incapable of describing. And this paper, famous paper published in the 1930s, became known as the EPR paradox, the Einstein, Podolsky, and Rosen paradox. And it caused a big stir at the time. It even made the front page of the New York Times. So Einstein, who had helped create quantum theory, was attacking it. Well, Einstein's objections were not strong enough to keep quantum mechanics from becoming an accepted theory. It did a great job of predicting how experiments were going to work. And the fact that it might be a so-called incomplete theory of nature didn't really seem to matter since it was capable of giving correct answers to experiments. And Einstein's objections seemed almost more philosophical than practical. It didn't seem like there was any way to to distinguish uh, between whether Einstein was right or quantum mechanics was right until the 1960s when a Scottish physicist named John Bell came along and had a theorem called Bell's theorem, which we'll study this semester, that made a definite statement about certain experiments that you could do that could distinguish whether quantum mechanics was correct or whether Einstein's objections to quantum mechanics were correct and valid objections. And it turns out that the experiments that Bell proposed, or versions of them, could be performed. And in fact, we are in the process of performing a version of these experiments down in Wellesley's laser lab. And you can test to see whether Einstein was right or quantum mechanics was right. And it turns out that Einstein was wrong. So, in spite of his complaints about spooky actions at a distance, and it makes it seem like something that a measurement that you're making in one place has an instantaneous effect on a measurement on the result of a measurement made in a different place on the other side of the room. We're 5 meters apart. It turns out that spooky actions at existence really do exist, and it's still a deeply unsettling idea. But I hope to deeply unsettle you this semester by having you read some foundational works having to do with Bell's theorem and the EPR paradox. And perhaps the biggest big idea that I want to convey to you over the course of this term is the fact that not only is quantum mechanics weird and funny, but the weirdnesses actually can prove to be quite useful. And that's an idea that has only recently really come to the forefront. People have come to realize in the last decade or two um, that you can take advantage of the sort of strange rules of quantum mechanics to do things that would be impossible or effectively impossible to accomplish if the rules of the physical world were purely classical. And the applications that we're going to focus on fall in the realm of what's called quantum information. So when we talk about information these days, we're mostly talking about computers that are based on the rules of classical physics. So computers, the fundamental building block of a computing system is the bit, a binary digit, a bit. And a bit is something that is either a 0 or a 1. And so you have strings of zeros and ones that you can use to encode information in a string of zeros and ones. So you store, a music file or an image file or a document file. Ultimately, you're storing strings of things that are either 0 or 1. In quantum mechanics, of course, there's this possibility of superposition. So you can have systems that are linear combinations of zeros and ones, superpositions of 0 and 1s. So we can talk about quantum bits, or qubits for short. And qubits are bits that are implemented using quantum particles like photons. We're going to talk a lot about photons as our quantum particles, and we're going to think of photons as being able to serve as a qubit, as a quantum bit. And in particular, it's the polarization state of a photon. Photons can either be polarized, say, in the horizontal direction or the vertical direction, but you can create photons that are in a superposition state of being both horizontally and vertically polarized. And it's this superposition state that is going to end up being useful in these applications of quantum information, quantum computing. And the real power of quantum computing is not when you have a single quantum bit, but when you have a system of many entangled quantum bits. So if you have n entangled bits, it turns out that the computational power that you can imagine in such a system of entangled bits grows exponentially with the number of bits. So if you have 10 quantum bits, you can store 2 to the 10th times as much information as you can in a single quantum bit. And it's that exponential growth in the computing power of entangled systems of quantum bits that really has people excited, because you can imagine building quantum computers like the one shown here. They're fast becoming a reality. This is a quantum computer that has about 50 entangled quantum bits in it. And quantum computers hold tremendous, tremendous promise for solving certain types of problems that you could never imagine solving with any classical computer. So by the end of Physics 323, I hope to give you some insight as to what all the excitement about quantum computing is all about. So that's it for this introductory episode of What's the Big Idea? Hope to see you again soon. Bye bye.